Welcome back. We're going to continue our discussion of enolates in synthesis by looking first at the Claisen condensation. And don't worry, we'll get a practical application of kinetic and thermodynamic control after this. But right now, we're going to learn the second most important reaction in organic chemistry. Oh, by the way, the aldol reaction is the most important, both in biochemistry and synthetic chemistry. And the Claisen is a close second. Every lipid in your body was made using Claisen condensations over and over again. Even the fatty acids and the terpenes and steroids were all made using Claisen condensations to assemble longer chains. So what's going on in the Claisen condensation? We're starting with an alpha hydrogen off of, in this case, a different species, an ester. And you would think that the alpha hydrogen here would have a pKa of less than 20. Remember, for aldehydes and ketones, it was 20. But instead, we have the opposite. We have a pKa of 25 if you're alpha to an ester. Why? Why? Well, if you look in the book, you'll see that the enolate that you create, in this one we have this enolate right here. Why are enolates more stable than other carbon anions? It's because they can resonate. Oh, they're not going to resonate that way. They can resonate this way and generate the more stable enolate down here. Double bond, ene, resonating O minus, olate. But same species with an oxygen next door, which has a lone pair, has two if you're counting, has not helpful resonance, but competing resonance. Competing resonance. That's not helping our enolate resonance at all. My old starboard used to do this too. Jump that down on the page for me because I hit a button. It's fun. Where were we here? There, we were here, weren't we? Competing resonance. It's not a good thing. So, yeah, I know that resonance form's better than the second one, but still, any competition means the other minus can't resonate. When this lone pair is resonating, that means this one can't. So this lone pair has less resonance contribution down here than it would if it was an aldehyde or a ketone where there's nothing competing on the other side. I don't want to belabor that point. We have a new number to remember. It's 25 for esters. And we'll see this 10 thing coming up very soon. So another thing we have to keep track of is the fact your choice of base for this reaction is limited. If you use a hydroxide base, don't use OH minus. Because this would compete and you'd have a second step. And we have a name for that reaction. Wow, pen's off. Don't use OH minus. We'll put a little star here. No, we use stars. We use a little telephone pole. No, we've already got a double telephone. We'll do triple telephone pole. It has competing saponification. Yep, saponification's on our test too. So a question you should ask yourself right now is, why is that not going to be a problem also with this base? And it is a problem with that base. But I want to ask you, what would the result be if instead of a hydrogen here, you had an ethyl? You'd get the exact same molecule you started with. So even if saponification happened 1,000 times before you deprotonated an alpha position, which is what you want to happen, then you would not even know that. So the base you choose must match the leaving group, because there is a competing reaction where there's a hydrolysis of sorts, would be a ethoxydolysis, creating the same ester you started with. So who cares, right? So make sure for Claisen condensations, your leaving group, see it leaving right, that's not leaving. Well, it's not leaving because we're not showing it, but if it left and was replaced by this, it's the same thing, which is what we want. So how does the mechanism work? It starts off just like the aldol. We generate enolate at the alpha position, which can resonate with the O, like over here. The enolate is a nucleophile. The pKa situation says we went from 25 to HOET, which has a pKa of 16. 25 to 16 means the difference is 7. No, 9. 25 minus 16 is 9. That means I have 1 billion of these that did not react for every one of these that did. So like in the aldol situation where the enolate was surrounded by unreacted carbonyl, it is even more so the case in this story. This enolate is swamped by 1 billion of these. This one is surrounded by 1 billion, and it does a reaction that we've seen many times. Attack, electrons up, come back, leaving group leaves. We even have it over here in our competing reaction. And you make this thing that looks like the final product. In fact, it's identical to this final product. You say, why am I doing more chemistry when I've already got my final product? It's a valid question. Well, it's a valid question with a valid answer. You can't escape the laws of pKa. Unlike the scenario over here where we have competing bad resonance, if I generate an enolate here, it can resonate with that carbonyl, come back, and then resonate with the other carbonyl. This is double the fun resonance here, twice as much stabilization. So that pKa goes all the way down to 10. Add that to your list of new pKas. They're right here. Go ahead. We've got about 4 10s or 5 10s right now. What do we have? Our first 10 was an ammonium ion, ammonium. Our second 10 was a phenol. And our third 10 was a thiol. And what was our fourth 10? Is this our fourth 10 or our fifth? I'm going to put it down as 4. There might have been another one. Okay, lots of 10s. So what's going to happen? Well, you can't stop this acid-base reaction from happening. 10 has to go to 16. So when you want to make your beta keto ester Claisen product, you've got to put the H back on that you just took off. So there it is. You're putting HCl in as a second step, and you generate a beta keto ester. They're very useful molecules for reasons you will see later. So let's do this. We're going to react 1 propanol with potassium dichromate in aqueous sulfuric acid. This looks a lot like a problem set, doesn't it? So you hunt around, you forgot what potassium dichromate is. I hope you didn't. But if you did, you'd look it up. It's a problem set. You can look stuff up. And aqueous sulfuric acid. That's a chromic acid reaction. With alcohols, we're generating carboxylic acids when the alcohol is primary. So that is the first reaction. And then we're going to use diazomethane also on our upcoming test. CH2N2 with carboxylic acids. This generates a methyl ester. And you've got your O, and you got your CH3. I'll just write CH3. One of those blue H's should be the black H that used to be on the carboxylic acid. You'll remember that when you review the mechanism. So I'm supposed to predict the product when the final product above is treated first with sodium methoxide and then with hydrochloric acid. Give a mechanism. So it's basically one carbon short of this one and a slightly different ester, but it's pretty much the same thing, isn't it? Good, it's all one piece. And we're going to react it with, remember what I said about choosing a base appropriately? Did I follow my own instructions? Sodium methoxide is really methoxide. I stopped hearing the word sodium about 10 years ago. It's a spectator. And follow the scheme up there for the mechanism. First step, take the alpha H, generate the enolate. Could have pasted it. What's the enolate going to attack? Chapter 19 is all about enolates attacking stuff. Well, it's surrounded by unreacted ester. Here's the ester. Shrink it down a little bit. We get a little yellow box going here. Limit where I'm going. Attack. Now you got to be careful here. I'm going to say red first, blue second. And the blue comes in right here when the leaving group leaves. And you make what looks like the Claisen product. We got this. Here we go. Got our new bond right here. And go blue here. Three carbons. So this species is right here. The attacked species without its leaving group. We're going to need its leaving group because that's a strong base in the presence of an acid with what pKa when it's alpha to 2 carbonyls? You got it, 10. Generating an enolate, resonance stabilized enolate. And we're going to have this product here. With an anion right there. Very stable anion, lots of resonance. And it's going to pick up a proton because we're then with means a separate step, hydrochloric acid. And you generate this species over here. I think we better draw it. first mechanism and draw your resulting product. You can go like this for a short form. Claisen products are beta keto. Now, if your enolate was an ester, then you have a beta keto ester. It depends on what your enolate was, how this ends. If it was an aldehyde enolate, then you'd have a beta keto aldehyde. The names of the reactions, and this is where students trip up sometimes, the names of the reactions, the aldol and the Claisen, they don't refer to the enolate that's doing the attacking. They refer to what's being attacked. If you're attacking an ester, it's called a Claisen reaction. If you're attacking an aldehyde or a ketone, right over here, here's the attack step. We're attacking a ketone. It's an aldol reaction. Similarly, down here, or on the previous page, I don't think we have a previous page. So on the previous day, Monday, we were attacking nothing but aldehydes and ketones. That's why we were calling them aldol reactions. So they're named after what they attack, not what the attacker is. All right. And we make a beta keto ester. That's this thing right here. Let's have a nice box. We haven't used nice boxes lately. See how nice it gets. I think it's going to erase a lot of stuff. Looks sweet. Not bad. Worth the wait. So you see that there's 2 3-carbon fragments in the product because they came from the same molecule, didn't they? This methyl propanoate. All 6 of those carbons come from that. 1, 2, 3, and 1, 2, 3. The leaving group on the second one is gone because it got attacked here. So Claisens, useful reactions. Aldols, also very useful reactions. We'll talk about the directed Claisen condensation now. And then we have a sample that we'll do to finish the segment where we take advantage of our new knowledge of thermodynamic versus kinetic control. So let's just look at what we're doing here. Once again, if you tried a simple Claisen with 2 different esters, you'd get the dog's breakfast with 4 products. So you can't do that to make not simple Claisens happen. We have to do what's called the directed Claisen, just like we did the directed aldol. We're going to use our new friend LDA, strong base, only knows how to take unhindered alpha H's. And it's going to grab this alpha H here, generate an enolate as we see here. And it's going to attack whatever we add. But don't forget, this is a 100% reaction. It's over. Step 1 is over when you generate the enolate. Then you have to give something to the enolate for it to react with. In this case, I'm going to use this ester over here, which I've drawn out over here. Ethyl attached to O attached to carbonyl. That's this, ethyl, O. One of the other O's is the carbonyl. And then an isopropyl. Then an isopropyl. Electrons attack. They come up. Lone pair comes back, kicks off the leaving group, generates an alpha H that's alpha to 2 carbonyls. pKa is 10. You cannot stop there. The base you just generated with this leaving group is a strong enough base to quantitatively take that H off and create only this product. That's the end of step 2. Step 3 is done to put that H back on. And that's what's happening here to make our beta keto ester. Are you surprised? There's alpha, there's beta, just like on the previous page. We had alpha and beta. Alpha's here, alpha to the ester, On the beta positions, a ketone. And same thing here. We have the alpha position to the ester, and beta is a ketone. Alpha and beta. Here I started with the other ester, and LDA, I know it's pretty picky about picking H's that are unhindered. It has no choice here. It'll probably be a little slower, this reaction, but worth waiting for. You've got to grab an H from a somewhat hindered position, but there's no other H's for LDA to grab. So you're going to wait for it to knife its way in there, the right angle, and it'll get the H off. So you generate an anion right there that attacks this ester, which looks like this, I promise. And you generate the bond from the alpha positions to this carbonyl here. And there it is, the carbonyl with the propyl on it. OET's gone. Similar mechanism over here. And there's a question here. Where is step 3 in the second example? Well, when you get to this stage here and it's over here, is there an alpha hydrogen to be had here that's got a pKa of 20? The answer is no. Is ethoxide going to take substantial amounts of this alpha H off? Not really. That's a pKa of 20. It's only alpha to the ketone. So I'm not worried about ethoxide taking that H off. So ethoxide has no H alpha to 2 carbonyls to deprotonate, so it won't do it. Easy speasy. So let's move this one to our next page, although I think I already have something on the next page. Let's do something fancy. Switch these. And we'll do this separate. Previous page, there's the introduction to the exercise. It will stretch it out. Excess LDA in sequence 1. So my question for you, LDA is plenty strong to take the H alpha to an ester, even though the pKa is up to 25. Which of these 3 alpha H's is LDA taking? The answer, it only knows how to take this one. Given a choice between a less hindered alpha H and a more hindered alpha H, LDA is going to go for the less hindered one. And when there's an excess of LDA, this is sequence 1, give a mechanism for the first sequence, might as well do it. Sequence 1, you've got your N minus with 2 isopropyls, grabbing that alpha H, and that's the end of step 1. Species you generate is this one. And I'm going to do a little rotation of sigma. There's the ethyl up there now. And how many CH2s after this position? 1, 2, then the C minus. 1, 2, C minus. And then we can go ETO2C for short form. And that's our nucleophile. And that's 100% yield. There's no equilibrium in this process. Why not? Because I used an excess of LDA, I'm going to have all of these react, and only whatever everything except the excess here reacts to make quantitatively this enolate. So it has no choice. It can't establish an equilibrium with the other enolate. There's no more H's to take. It's going to do this. Red first, blue second. And lone pair is going to come back. And kick off our leaving group. And you think you're done. This is the number one mistake I see. Students see that first product and they say, we're done. This is the second product, by the way. Flip the molecule over so you visualize the second product better. There's a ketone right there. There's your ethyl. No, I got the ethyl. I'm having trouble flipping stuff myself. And the CO2 ET's here. Oh, wait. This could be an example where we are done, right? Did I get the right product? I attacked here. I don't have, this is not the product. There's still H's on there. That flipping comment was out of line. This would give this, yeah, just I didn't move anything. But I just want to point out this is the mirror image of this. They're the same molecule. I do also want to point out that there's this very special H here that's alpha to both carbonyls, which means it's coming off. Why is it coming off? What's the other product you just made? OET minus. Strong base. Must come off. And you're making this. Now I'll draw what looks like the product at the top of the screen. Ugh. Why not? It's got an anion there. It needs to become this one. Predict the product for each sequence. There's my prediction. How do we get there? Step 2, HCl. Gets that product. And that is, we call that the kinetic product or the thermodynamic product? It's a good question. We call it the kinetic product. There was no equilibrium allowed to happen here. In the next reaction, you're going to generate less than a quantitative amount of the other enolate, of the original enolate, the same enolate, but because it wasn't 100% reaction, it's a 90% reaction. That means 10% of this is still unreacted. That C minus, instead of doing this deal, is in equilibrium by grabbing this H with the other enolate, which is more stable. The enolate on this position would have more carbons attached than the enolate on this position. So that's why in sequence 2, we get the other product. It comes from the more stable enolate, where equilibrium allowed the more stable enolate to occur. How did we make that happen? We used a limiting amount of LDA, and that establishes equilibrium between the two different enolates. And it gives us this more thermodynamically stable, well, the enolate was more thermodynamically stable, and this is the product that results from the enolate. And that there is a good spot to stop for this segment, and we'll pick it up after the break.